Hello everyone, welcome to this video. In this video, we are going to see how to solve a first order nonlinear PDEs. So in the last video, we saw how to solve the type 1 form of first order nonlinear PDEs. So in this video, we can see how to solve the type 2 form of nonlinear PDEs. The type 2 form of nonlinear PDE is also known as Clairaid's form. So this is what the form of nonlinear PDE, that is z is equal to px plus qy plus function of p and q. So here the first two terms are fixed. So this is what the exact form of second type of nonlinear PDE. So here we have z as px plus qy plus some function of p and q. We know that here p is dou z by dou x and q is dou z by dou y. These are first order derivatives, and here the solution is obtained as follows. So for the second type of nonlinear PDE also, we assume the solution is z is equal to ax plus by plus c. And from this, when you partial differentiate this z with respect to x, we get dou z by dou x as a and dou z by dou y as b. So now we give the substitution for p as a and q as b here. So when you replace p as a and q as b, so that we get our complete solution as in this form, that is z is equal to ax plus by plus function of a comma b. So for the type 2 form of nonlinear PDEs, the complete solution is obtained just by replacing p as a and q as b in the given equation, and then differentiation of this complete solution partially with respect to the arbitrary constants a and b. We can find the resultant equations, and so elimination of those constants a and b from the resultant equations gives the singular solution, and then the general solution is obtained as usual. So now we'll see how to solve the second type of nonlinear PDE. So this is what our first example. So here the question is solve z is equal to px plus qy plus function of p and q. Here it is 3 into p into q. Okay, so here we have the second type of nonlinear PDE, and this is known as Clairaid's form. So here we assume the solution is z is equal to ax plus by plus c, and because by this assumption we get p is equal to a, that is dou z by dou x is a, and q is equal to b, that is dou z by dou y is q, dou z by dou y is b, which is nothing but q is equal to b. So now we are substituting this in the given equation to get our complete solution. So in the second type of nonlinear PDE, just by replacing p as a and q as b, we get our complete solution. So here the complete solution is z is equal to ax plus by plus 3 into ab. So now we got our complete solution. The next step is finding the singular solution. So to find the singular solution, we have to differentiate this complete solution with respect to the arbitrary constants a and b partially. So now differentiating this equation 2 partially with respect to a, we get the left hand side is dou z by dou a is 0, and in the right hand side we have x plus second term becomes 0 as there is no a in that, and in the third differentiation of a becomes 1, so it is only 3b. Similarly, differentiating this equation 2 with respect to b partially, the left hand side is 0 again, and because that is a function of x and y only, so dou z by dou b means 0, and in the right hand side, the first term there is no b, so that becomes 0, and in the second there is b, that becomes 1, so it is y, plus in the third differentiation of b is 1, so it is only 3. So from this we write the constants in terms of x and y, and when you replace these in the complete solution we get the singular solution. So from the first we get 3b is minus x, from this b is minus x by 3, and similarly from the second we get 3a is minus y, and this implies that a is minus y by 3. So now we are going to substitute these two in the complete solution. Therefore, now substitution of these two in the complete solution gives z is equal to a is minus y by 3, so it is minus y by 3 into x, plus b is minus x by 3 into y, and plus 3 into a is minus y by 3 and b is minus x by 3. So upon simplification we get it is minus xy by 3, again minus xy by 3, and here it is plus xy by 3. So here we can cancel one xy by 3 as we have both positive and negative sign. So this is what our singular solution, that is 3z is equal to minus xy, or 3z plus xy is equal to 0. Since this solution doesn't involve any arbitrary constant, this is what our singular solution. So this is what our singular solution. And for finding the general solution, so for finding the general solution, we take b as a function of a. We have to uh, take one constant as a function of other. So if we take z as ax plus that b is taken as f of a, then it is f of a into y plus 3 into a into f of a. If you take b as f of a in the complete solution. So this is now we have, and now differentiation of this with respect to a partially. We'll get one more equation and elimination of a, from that elimination of a from those equations gives the general solution. Okay. So here we have to write one more step in which we are going to write the differentiation of this equation with respect to a partially, and then elimination of a from the last two gives the general solution. So now let's see another example. So this is what our second example. Solve z is equal to px plus qy. The first two terms are fixed, and then we have a function of f of p comma q. So this is in Claride's form. So we have a second form of PDE. So for solving this, we consider our solution as z is equal to ax plus by plus c. And from this assumption we get p is equal to a and q is equal to b. So substituting these in our given equation 1, we get our complete solution as the complete solution of the given is z is equal to ax plus by minus 4 into a square into b square. So for the second type of nonlinear PDE, the complete solution is easily obtained just by replacing p as a and q as b in the given equation. So now for finding the singular solution, we differentiate equation 2 partially with respect to the arbitrary constants a and b. So now differentiation of 2 with respect to a partially, we get 0 is equal to x minus 8ab square, and with respect to b partially we get 0 is equal to, here the first term is 0, and differentiation of the second with respect to b partially it is y minus differentiation of the third term with respect to b it is minus 8a square b. So from this we try to express a and b in terms of x and y. But from the first we can write 8ab square is equal to x. And this implies that 8ab is equal to x by b. And from the second we can write 8a square b is equal to y. So from this we can write 8ab as y by a. So now comparing these two we can write x by a is equal to y by x by b is equal to y by a. Since these two are equal, we can say this is equal to some constant k. So from this we get x as b into k or b as x by k. Actually, we want the substitution for the constant terms in terms of x and y. So here b can be replaced by x by k. And similarly, we get y is equal to ak or a is y by k. So when you replace the constant a and b in terms of x and y, still we have one more constant involved in that, that is nothing but k. So here we are going to find out what is the value of k. For we can consider any one of the previous equation that we are going to give this substitution. So if we substitute a and b in this, what we are getting, it is 8 a is y by k and b square is x square by k square is equal to x. So we can cancel 1x from here, and from this we get 8xy is equal to k cube. 8xy is equal to k cube, or from this we get k is equal to 2xy the whole power 1 by 3. So we have got the substitution for k. So now using this substitution here, we get b as x by 2 into xy the whole power 1 by 3, and a is y by 2 into xy the whole power 1 by 3. So upon simplification we get b is equal to 1 by 2 x power, when you take this xy the whole power 1 by 3 to the numerator, it is x power 1 minus 1 by 3, that is it is x power 2 by 3 into y power minus 1 by 3. And we get the substitution for a as 1 by 2, y power 2 by 3 and x power minus 1 by 3. So now we are going to replace these a and b in the complete solution. Okay, and we are going to eliminate these constants in that to get our singular solution. So now replacing here we get z is equal to, so what is our a? It is 1 by 2, 1 by 2 y power 2 by 3 x power minus 1 by 3 into x, plus b is 1 by 2 y, and it is x power 2 by 3 and y power minus 1 by 3 into y, minus 4 into a square is 1 by 4 and y power, it is y power 4 by 3 into x power minus 2 by 3 into 1 by 4, b square is 1 by 4, x power 4 by 3, x power 4 by 3 into y power minus 2 by 3. So upon simplification of this, we get z is equal to 1 by 2 x power 2 by 3 into y power 2 by 3 plus 1 by 2 x power 2 by 3 into y power 2 by 3 minus 4 minus 1 by 4 into x power 2 by 3 and y power 2 by 3. So here we have, summing up these two, we get x power 2 by 3 into y power 2 by 3 minus 1 by 4 into x power 2 by 3 into y power 2 by 3. So it is 1 minus 1 by 4, that is 3 by 4, x power 2 by 3 and y power 2 by 3. This is what our x, or else we can, this is what our z, or else we can write, this is taking cube on both sides, it is z cube is equal to 27 by 64 into x square and y square. So which gives our singular solution. So this is what our singular solution, and the general solution is obtained just by considering one constant as the function of the other. So our complete solution is z is equal to ax plus by minus 4 into a square into b square. So in this, if we replace b as function of a, then we get z is equal to ax plus f of a into y minus 4a square f of a the whole square. So now differentiating this partially with respect to a and elimination of a gives our general solution. Partially and elimination of a gives the general solution. So now let's see one more example in this. So this is our next example. So this is also in Clairaut's form because the first two terms are fixed, that is px plus qy plus some function of p and q we have. So which is also a Clairaut's form of nonlinear PDE. So here the solution is assumed as z is equal to ax plus by plus c, and from this assumption we get p is equal to a and q is equal to b, and substituting this in one, that is in our given equation, we get our complete solution. So the complete solution is z is equal to ax plus by plus a square minus b square. So now we are moving on finding the singular solution. For we have to differentiate this complete solution with respect to the arbitrary constants a and b. So differentiation of 2 partially with respect to a and then b, we get 0 is equal to, in the right hand side we get x, second term becomes 0, and in the third we have, it is only 2a and minus b square becomes 0. And similarly, when you differentiate the second equation with respect to b partially, we get 0 is equal to y minus 2b. So this implies that we get our 2a is minus x. This implies that a is minus x by 2. And from this we get 2b is equal to y, and from this b is equal to y by 2. So now substituting this in the complete solution, we get, it is z is equal to a is minus x, so it is minus x square by 2, and plus b is y, so it is plus y square by 2, minus, it is a square by 2 is plus a square by 2, so it is x square by 4 minus y square by 4. So upon simplification we get 4 is 8, 4 is 8, or here we have 1 by 4 minus 1 by 2 for x square term. So it is 1 by 2 x square, and 1 by 2 minus 1 by 4. So it is 1 by 4. So here it is minus 1 by 2 x square and plus 1 by 2 y square we have. sorry, minus 1 by 4 x square and plus 1 by 4 y square we have. From this we get 4z is y square minus x square. So this is what our singular solution. Since it is free from arbitrary constants, so this is what our singular solution. And for the general solution, we take a as a function of b or b as a function of a. That is, since our complete solution is z is equal to ax plus by minus plus a square and minus b square, in which we take b as function of a, that is z is equal to ax plus f of a into y plus a square minus f of a the whole square. So now differentiation of this with respect to a partially, we get 0 is equal to x plus f dash of a into y plus 2a minus 2 into f of a into f dash of a. So now elimination of a from these two equations gives the general solution. Now elimination of a from 3 and 4, we get our general solution. Actually, here we don't know what is our function of a. If you know what is our function of a exactly in terms of a only, you can differentiate. Otherwise, you can write like this. So elimination of a from the last two equations gives our general solution. I hope you understand how to solve the second type of nonlinear PDE. So let us meet in our next video. Thank you.